Good evening, everyone, and welcome to today's session on AI and ML. I'd like to introduce today's presenter, Sayan De, a data scientist and analytics expert with a decade's worth of experience. Sayan has spanned a multitude of roles as a corporate trainer, developer, project manager, scrum master, and client engagement manager. Besides consulting at organizations like Walmart and Intuit, he also works on high-end projects in the areas of computer vision and natural language processing. He has a unique blend of production experience in cutting-edge AI solutions and coaching experience through his associations with several of the world's top training providers, both in the online and offline formats. Sayan is an active speaker at global technology events and seminars and is a passionate evangelist of advanced technologies in the data science technology stack. Before we start, I would like to inform you to ask questions in the Q&A tab. We will address them at the end of the session. Also, in order to help us to continue to make our programs better, we request you to please take the short survey at the end of this webinar. Sayan, we're glad to have you present at the Online Manipal Plus series. Over to you.
Right, thank you so much, and welcome all of you. Good evening, everybody, for joining in, and and wonderful to have all of you in as part of this session. Hi, all of you, everybody. Hello, everybody. I hope all of you can see me. So, looking forward to make this session very exciting and very lively for all of you. And it's a short session, and we'll be starting off with giving a very basic rundown on what machine learning actually is, what artificial intelligence actually is, and we'll be looking at lots of practical applications of where AI/ML is actually used. I'm very sure that given the buzzwords that you're hearing in today's world, I'm very sure people have generally heard of these terms multitude of times. We'll try to start off with some general examples and then get a lot into the technical details of how these things are done. But generally speaking, one thing that we'll try to do is try to give you lots of use cases on the advanced side of things. I'll try to bring up some cool examples on computer vision, face detection, object tracking, some of the things that we get to see in day-to-day lives, and we'll try to add in some interesting examples on those ends. So without any further ado, let's get started. And when we talk about the term AI, when we talk about the term artificial intelligence, what do we mean by the term artificial intelligence? What do you mean by the term AI in the first place? So anything, AI is basically anything that you can use to. So we all have living intelligence. So we all have living intelligence, as in human intelligence is what we all possess. Okay, if I can basically induce that same intelligence in a robot or a machine or an artificial agent, that is simply what we refer to as artificial intelligence. The term AI was basically coined in 1950s. There was a Dartmouth conference that happened where the term AI was first coined, where the founding fathers or the pioneers in the field got together and they came up with this particular term called artificial intelligence. And the basic idea was to basically make machines do things that humans can do, that humans were previously doing. How do we automate certain tasks? How can we make machines reasonably intelligent so that whatever tasks humans were manually doing historically, can we make machines do that thing? And that's for the whole origin of the term AI around that time. And remember, 1950s was an era when everything was pretty. There were no computers back then. There were no calculators back then. We're talking about a very traditional era. The world's first computer system, ENIAC, came around that time. Boolean algebra was just starting to get developed around that time. So that is the era when the term AI was basically coined. So now the next thing is basically ML. When you talk about machine learning, this is typically a Venn diagram that all of you would have come to. And I'm coming to that, Sonali, on that question. We have all seen this Venn diagram or heard of this Venn diagram in some capacity. And again, as I say, because of this particular hype that we are seeing in data science and machine learning and AI in today's world, people typically tend to use both these terms together. So we say AI is the same thing, ML is the same thing. In fact, there are many courses that go like AI, ML. So one of the things I'll try to do right up front is try to clarify what is AI versus ML? What is the actual difference? So if you can induce intelligence in a non-living being, that is for artificial intelligence. That's the broadest way to look at it. But what is machine learning? Machine learning is a subset. So to understand this a little bit more specifically, let's come to this particular whiteboard. I'll take a very simple example for you. Let's say I've got this AC at the top of my room. Okay, this is the air conditioner, and let's say I set this up to 24 degrees Celsius. Okay, I set this air conditioner to 24 degrees Celsius. When I do that, the AC works in an automatic manner, and if it senses that my room temperature goes below 24 degrees Celsius, it will basically stop cooling. And if it senses that the temperature goes above 24 degrees Celsius, it will start cooling. See, it is a very simple rule-based if-else logic that we have put in, using which the air conditioner is basically running. There is no machine learning happening. There's no intelligence. There's no sophisticated intelligence that we have built there. Okay, all that we are saying is we are basically talking about a specific form of AI which is based on rules, and hence we are talking about something called rule-based AI. It's an artificially intelligent agent where you have hard-coded certain specific instructions. There are sensors that are basically present, and on the basis of that, this whole thing is working. So you have simply hard-coded specific rules. You have told the machine that if you detect the temperature is going above this limit, do this, else do this. And that is what we refer to as rule-based AI. So it's a specific branch of AI, very basic AI, very naive AI, but not machine learning. So AI and ML are not the same thing. So there are a lot of examples of AI agents which have nothing to do with machine learning. Think about your automatic washing machines that you have in your homes. You press a button and something happens, right? So let's say you want to wash your clothes in monsoon mode or dry mode or whatever. When you press the button, the set of instructions are already stored. That means you're telling the machine what to do and how to do it. The machine will basically operate this whole thing on the basis of that. So that's the general idea behind what rule-based intelligence actually is. So the specific instructions have already been hard-coded as to how the washing machine will basically work. Okay, what the rinse cycle will be, what the dry cycle will be, how much of detergent to add. It will even detect the load automatically, and on the basis of that, the entire wash program will be automatically executed. And that is what we refer to as rule-based intelligence. You can think of something like your laptops or the mobile phones on which you're attending this webinar right now. The operating system that is powering our laptops and the mobile phones, be it the Windows OS or the Mac OS, that is a very sophisticated piece of software. Now, if you think about it, that software is actually an excellent example of rule-based intelligence. I'll tell you why. Because if your mobile phone battery goes below 10% or 15% or 20%, the battery saver kicks in. And when the battery saver kicks in, the screen will basically dim. The data sync will actually stop. Certain applications, background data will enable. And if you go to your camera and turn on flash, the flash will not work. Now, who has decided these things? It is an intelligent agent in a way. So the operating system is an intelligent agent, which has basically been pre-programmed, or you have hard-coded certain rules, and you have told the machine and you have told the operating system that, hey, when these things happen, do this. There's no special intelligence that is there. It's something that you have hard-coded in a way. Or you can talk about the thermal shutdown feature of smartphones. You try to take your smartphone over to keep it in the sun for a long time. What do you see will happen? After a while, you can't use the smartphone. The Android OS will come up with a message saying that you can't use your phone. The phone has heated too much. So please cool it down, only then you can use it. These are again simple examples of AI agents, where rules have been hard-coded. And that is what we refer to as rule-based intelligence. Okay, so rule-based intelligence is that kind of AI where you tell the machine specifically what to do and how to do it. You provide the rules in a very hard-coded manner, and the machine goes and operates on the basis of whatever rules you have provided. But one major problem with respect to rule-based AI would be that the rules are basically static and hard-coded. So it is something that you are hard-coding, and it is a static set of rules that you are providing. The rules are typically static and hard-coded in rule-based intelligence. And there are several, like we can talk about factory robots for that matter. You talk about factory robots, right? All these factory robots that you basically get to see, right? What kind of intelligence is that? What do you see in these factory robots? Now they seem to be absolutely like, like right straight out of Terminator. But is that really machine learning? Actually not. Although Fanuc is a very different thing. Fanuc is one of the industrial leaders in this space. But when you look at these specific examples of industrial robots are excellent examples of rule-based intelligence, where precision rules have been hard-coded, where you have told the machine what to do and how to do in a particular way, and the machine is working on the basis of that. It is an AI agent, but it is an AI agent that is based on rules or explicit instructions that you are provided. And that's the intuition behind what rule-based intelligence actually is. So now the question is, where does machine learning come in, and why do we even need machine learning? So this particular problem started to occur, especially once we started moving into more unstructured forms of data like images and text and videos. So as we started moving into more unstructured forms of data, like images and audio and video and text kind of data, we started to realize that it started becoming very, very difficult to hard code the rules, because we ourselves did not know what the rules will be. So what do you do in a situation when the rules themselves are very hard, when the rules themselves are very, very difficult, the rules themselves are unknown? What do you do in that kind of a situation? We can't hard code the rules, right? See, technically, whenever you write any program in this audience, whoever has ever written a computer program in their lives, be it in whatever language you've written, be it a Python or a Java or a C, C++, whenever you write a script or a program or a function, you're technically coding an AI agent. That program or the script is basically an AI agent. So you know the rules, you know exactly the specifications of what you have to do. So you have laid down the specifications and the agent works on the basis of that. But what if you don't know the rules? For example, what if I want to design a system that detects elephants? So let's say if you have to design a system that detects elephants, how will you write the rules? How will you write the if else statement in a way? So we'll say if the agent contains 2 tasks, 1 trunk, 4 legs, 2 eyes, 2 ears, 1 tail, then elephant else not elephant. And there are software, there are ways we can actually do that. But think about it. This is possible. This is doable. But will this set of rules always work? Maybe for a simple example like this, it is okay. But if you talk about more complex examples, that too in an elephant, a herd of elephants, if you look at, will this example work? Actually not. If you look at this picture right now, if you look at this particular image or any image, if you look at this image right now, or if you look at this particular herd of elephants right now, this one, if you take a look at right now, okay, if you look at this one right now, will our rule work in this case? Not really. So look at elephants in the background right now. This elephant does not even have a tusk. This elephant, we can't see anything. There is no trunk, tusk, eyes, egg, legs, ears, nothing we can see. So it's fine to define rules for proper explicit objects. But what if we can't even see the object? What if there are elephants in the background? Will those rules work in that case? No. So after a point, we are not even saying the rules are difficult. We are saying the rules are unknown. They are impossible. We don't even know what the rules are. Elephants may have tusk. Elephants may not have tusk. Although tusk is such a defining feature of an elephant. So what do you do in that case? It is an extremely hard problem. And if you go to language data, natural language data, if you say, okay, Google will authenticate your voice. It look at the speech patterns and try to predict, try to estimate that it's you. But can you hard code the rules? Can you really say if the data patterns, if the voice patterns are so and so, then it is Cheyenne, it is somebody else? Impossible. You can't do that because every time you speak, you're using a different pitch, frequency. The voice patterns are different every time. It's always unique every time. And still the machine is able to identify it's you, which is quite incredible. So these are challenges that you cannot solve. These are challenges that you cannot solve using rules. So that's exactly the inspiration behind machine learning, where we are saying that, okay, we don't know the rules. We can't hard code the rules. So we will give the machine lots and lots of data. I will give you lots and lots of input output combinations, X, Y, X, Y, X, Y, X, Y, X, Y combinations, and you learn the rules because I don't know the rules. And that's the crux of what we are trying to do in machine learning. The simplest possible example of what I just now talked about will be this one. All of you can see X, Y. So I give the machine lots and lots of these so-called XY combinations, 1, 2, 3, 4, 5, 6, 7, 8. Okay, the machine will learn from these specific XY combinations and use an algorithm to learn the model. I'm not explicitly hard coding that if X is this, Y will be what? If X is this, Y will be what? I'm not hard coding anything. I'm not explicitly hard coding any pattern. No, I'm not defining any rules. No, I have only provided the machine with lots and lots of input output example patterns. I leave it to the machine to use some algorithm to study those patterns, build a mathematical model, which is what we are looking at right now, y equal to x plus 1. That is the machine learning model that it has created. And now, given a new value of x, using that mathematical model, the machine will try to predict the value of y. And that's the crux of what we are trying to do in machine learning generally. Okay, and you can see a couple of jargons that we use here in this particular process. We have data. This is typically what we call the training data. In machine learning problems, we call it a training data. There is a specific algorithm that is learning the patterns. Although here it is quite obvious what the patterns are, we could just as well guess from with a human brain what the patterns are. But anyways, there's a specific tailored algorithm that we'll be using to learn these patterns. And this is basically what we call the model. Oftentimes models and algorithms are mixed and matched, but they're not the same thing. They're two different things. The algorithm is basically the logic that we are using, and the model is the final product that we are getting. Okay, the model is typically in the form of a mathematical equation or rules that we get, which in this case is y equal to x plus 1. Okay, and this process of learning the patterns from the historical data is what we call fitting, and making predictions on new data is what we call predicting. So fit on the data, build a model, and do prediction on the basis of using a new data. And that's the crux of what we are trying to do in machine learning. A very simple analogy, if I have to put it, would be machines learn the same way children learn, right? Machines learn the same way children learn. Machines learn the same way young babies learn, young kids learn, right? How do young kids learn? Young kids also learn from lots and lots of examples, right? And if you think about it, let's say you have a kid that is going to kindergarten for the very first time. How will you teach that kid? You're trying to teach that kid examples of apples and guavas. How does the teacher teach the kid? The teacher will show the kid lots and lots of examples of apples. That hey, fruits like this are apples, fruits like this are guavas, fruits like this are apples, and fruits like this are guavas. And the kid will learn from those input-output patterns. And these are the features of the fruit that they will look at: the size of the fruit, the shape of the fruit, and the color of the fruit. The size is small, the shape is round, and the color is green. It's a guava. The size is small, the shape is round, the color is red. It's an apple. And the kid will learn from those input-output patterns, and it will build a model. And that's how machine learning is basically happening. So machines are learning the same way that a kid is basically learning, from lots and lots of examples. It is not that the teacher has hard-coded some logic in the kid's head and the kid is learning based on that. No, but the kid is learning by seeing lots and lots of examples. And the more examples you show the kid, the better the kid will learn. So the more examples you show the machine, the machine will also learn better. So for example, at this particular point in time, the kid knows that there are apples and guavas that are possible. Now, if you show it a very different kind of fruit, let's say you bring a jackfruit from somewhere and you show the kid that, hey, what is it called? The kid will not know, because you haven't even told the kid what a jackfruit is even called. So the kid doesn't even know that there's something called a jackfruit exists. So the moment you want, so the kid is only as good as the quality of the data that you have provided to it. Okay, and hence the crux of machine learning, where we say that there is some data, there are lots and lots of these input-output combinations. You use some algorithm, and in the process, you try to build a model. Okay, now, generally speaking, there is one other term that we use in this particular space called DL, deep learning. So what is this entity called deep learning? Well, deep learning in this case would be basically where we try to, we have a deep learning algorithm generally. So deep learning will be more on the lines of where instead of using a machine learning algorithm, we can also use a deep learning algorithm. So the terms can be interchangeably used. Everything generally remains the same. Okay, the data component will remain very, very similar. However, instead of using a machine learning algorithm, we can use a deep learning algorithm. And in the process, you can build a deep learning model. But the whole idea will be very, very similar. Here also, you're learning from lots and lots of XY combinations, input-output combinations. Okay, fruit, apple, fruit, guava, fruit, apple. You're learning from lots and lots of combinations. Use a particular algorithm and build a model. Okay, if you're using a machine learning algorithm, you will end up building a machine learning model. On the contrary, if you're using a deep learning algorithm, you will end up basically building a deep learning model. A DL model is what you will end up building. The only general conceptual understanding of deep learning will be that when it comes to using deep learning algorithms, we typically use neural networks. Just keep that at the back of your mind that deep learning algorithms use neural networks behind the scenes. However, having said that, deep learning is more suited to problems on computer vision and natural language processing, which is pertaining to image data, text data, and different forms of unstructured data, where the data patterns are much more complex. So machine learning is more suited for structured data, tabular data, simple data sets, whereas deep learning neural networks will be more tailored towards image data, text data, and unstructured data, where the patterns are much more complex. And because the patterns are much more complex in elephant detection and those kind of things, you want to use a more complex set of algorithms bordering on neural networks to learn those specific data patterns. And hence the general idea behind deep learning. And if I have to add one more set here, there is AI, there is ML, and inside that you will basically have something called DL. Okay, so there's AI, there is ML, and inside that you will have DL. So deep learning is a more specialized form of machine learning, as we call it. Okay, so that's the general idea behind what these three jargons actually mean. So AI is a superset. How do we make machines intelligent? So we can make machines intelligent using basic rules, static hard-coded rules. But when the rules themselves are unknown, we can make machines intelligent using machine learning, where the machine learns what those rules specifically will be. That's the intuition. Okay, that's how we basically go back and look at what these terms actually mean generally. Now, let me show you a classic case of machine learning here. And a couple of things that I wanted to clarify is machine learning is, of course, error prone. Okay, unlike rule-based AI, machine learning is prone to mistakes. Okay, because the machine is learning the patterns. The machine is learning the patterns here. There is a possibility that whatever patterns it has learned might be wrong. So machine learning systems are fundamentally error prone. And this is manifested in several real-time examples, which I wanted to show you at least a couple of them here. So for example, we can look at, this one. This is a very famous one where Google made a blunder. They basically predicted a black person to be a gorilla, actually. Okay, so I'm just trying to open up this example. So Google predicted a black person to be a gorilla. And this happened back in 2015, where Google's, so this black software engineer took a selfie, and Google Lens predicted this person to be a gorilla, actually. It was using computer vision, and this became quite a story around that time. And even today, if you go to Google Photos and try to search with gorilla keyword, it will not work, actually. Okay, and if you think about it again, from a technical perspective, why this particular thing went wrong, the main issue, the main reason why this particular system went for a toss is because of the quality of my data. It again goes back to the fundamentals and the foundations we discussed in our session. Data algorithm model. So ultimately, we are talking about building a good quality model. The model has to be good quality. But if your data itself is biased, the model will be biased. The quality of my data was very bad in this case. Algorithm was good, but the quality of my data was very bad. So Google's model actually failed because the quality of the data was very bad. And if you read the main article about Google gorillas, what actually happened, you will realize that the example data that Google actually used, in fact, what was available, anything that resembled black, if the skin color and the pigments were black, that was typically resembling of gorillas, chimpanzees, and animals. And anything that was white was basically humans. That was the nature of our training data. The training data itself was highly biased. Now you don't even have to think of machine learning. Think of it like a small kid. Imagine you have a small kid at home and you're telling the kid that, hey, if you look at something white, human, if you look at something black, gorilla. What's that? Okay, so if you look at something white, human, if you look at something black, gorilla. That's one way to look at it. So machine will learn on the basis of those specific patterns. Okay, and even now, if you go and search for it, even now, if you basically go and search for these particular patterns, you will see. Okay, you will actually see. Like if I just go and search for people, I'm just giving a general example. If you search for people on Google, you will actually see that most examples are white. Like we don't see any black people, right? I'm just doing a simple Google search just to show you how data is biased generally. Like the data that is available around us, around you and me, they're just generally biased. And if you're training your machine learning models using this kind of data, then the models will also inherently be biased. Something I wanted to just introduce you to as you're building, as you're getting towards building more complex systems, that this could be an issue that can come up in real world scenarios. That data, if your quality of data is biased, your machine learning models will also be biased. And finally, if I just quickly share with you another example of CEO, let's say. Okay, if I search for CEO, so what are the patterns that you're seeing right now? A, they're mostly male, B, they're mostly white, and C, they're mostly wearing a blazer. The first 10, 15 search results, if I just search, so most of them are males, most of them are white, and most of them are wearing a blazer. These are stereotypes that are available as part of my data. And my models are learning on the basis of the stereotypes. Errors in machine learning can happen in a lot of other ways. A few of these examples I wanted to also point out. This is my own Google Photos account. And see how beautifully the model actually identified examples of snow here. I searched for snow on my Google Photos account. It did identify snow very well. It is actually using machine learning entirely. Your Google Photos is a classic example of machine learning, where it is you search for certain keywords and Google will identify, okay, the keywords here. But then it didn't quite work here. Look at this. I took this picture from the flight and it somehow identified, it somehow identified, sorry, just give me 1 minute. It somehow identified the clouds. It mistook the clouds to be snow. So this was a mistake that Google actually did in this case, right? So these are, again, classic examples where errors can crop up in machine learning, which is what we're able to see right now. So mistakes can happen also in ML. The same reason why Tesla cars, if you've come across these news stories, they often crash. Reason why Tesla cars crash is because oftentimes the models are unable to detect certain stop signs or certain, certain road signs, and they make a wrong turn and things like that happen. The same reason why models are prone to errors. Okay, I'm searching for elephants right now in the screen. Model did detect an elephant very correctly here. Elephant detection happened very correctly here, but the model was somehow unable to detect elephants here. This was Singapore Zoo, where I visited some time back, and somehow the model thinks that there are elephants in the screen right now. There are no elephants here, but somehow the patterns and the pixel patterns, it somehow thinks that there are elephants in the screen right now. There are no elephants right now, actually, you can see. But maybe what might have happened is if you just scroll all the way down, zoom all the way into this particular picture, maybe the pixel patterns here resemble an elephant. Maybe very vaguely they resemble an elephant. That's why the Google model is confused. Okay, or maybe even if you look at this particular picture, this is night safari, not this one, sorry, this is correct detection that happened. If you look at this one, this is night safari, and maybe here also Google thinks that I'm looking at an elephant. It's not correct. There are no elephants actually. There's something else. Okay, elephant. They're not elephants, but maybe somewhere the pixel patterns resemble that of elephants. So Google is again confused. And the interesting part is these models are always dynamic. Like if I open my Google Photos a week from now, a month from now, the results will actually change. Google is constantly updating its models. And in case people have never used Photos before, it's an incredible application. You must use it. There are so many different things you can search. You can search for skyscrapers. You can search for a whole lot of incredible things actually. Okay, so this is all machine learning that is happening, because it is not possible for a human expert to do all this. It's not possible for a human expert to manually sit and do all this, right? So you can actually see. So how do you go back and do all this stuff, right? For example, look at this one: forests, cars, temples, Christmas, zoo, lakes, palaces, Diwali, right? Cooking, monuments, fog, farms. So it's not possible for a human being to sit and write rules and logic for all of this. This is obviously based on my account and my photos and everything. But see how incredibly Google Photos can go back and do all these things. Okay, there'll be some resemblances based on skyscrapers, towers, and all that, but these are again classic examples of how machine learning is practically used in a way. Okay, all right. So now, okay. So now with this particular context in mind, let's move on. Let's move on to the next phase of our conversation. Now that we understand a little bit about what is AI, what is ML, and we have a general understanding of this whole thing, I wanted to focus a little bit on the uh, the computer vision side of things, right? What are the different types of computer vision problems that we have? This is the most exciting field of research that we are seeing in deep learning today, computer vision. And what is the meaning of computer vision? What do you actually mean by computer vision? What do we even mean by computer vision? So what is vision in the first place? Vision is basically defined as the ability to see and perceive things. So what is vision? Vision is basically the ability to see and perceive things. See, even a person in a vegetative state, a coma state, even that person can see things. So, but what is vision? Vision is being able to see and perceive. Can you see and can you understand what you're seeing? That is exactly what vision actually is, in a way. If I can give computers the same ability, that is what we call computer vision. See, I can take my smartphone and I can click a picture. That is not vision. Okay. See, so I can basically take a smartphone and I can basically take so I can take a smartphone and I can basically take a picture. That is not vision. That is just seeing, right? But if I can take that picture and if I can use Google Lens, that is what we will refer to as computer vision. Because now we are not only seeing, but we're also perceiving what we are seeing. Because Google Lens can look at that photo and it can do a whole lot more with that picture. People who have used Google Lens will know that Google Lens will not only look at that picture, but it will tell you what is there in the picture. It will identify text in that picture. And these are all incredible examples of computer vision, machine learning. because you cannot do it manually. You cannot potentially manually look at a text and try to write rules around it. Incredible applications of machine learning in everyday gadgets we're able to see. Okay. And talking about Google and talking about smartphones, speech to text. Obviously, that's another incredible application that you will typically see. So from an application perspective, there are many applications that we have in ML. And if I have to just talk a little bit about some of them before I go to the computer vision side of things. So we have Siri, we have voice assistants, incredible applications of machine learning, right? So voice assistants are there where you can just say something, Google Assistant, you can give it a range of instructions, and the assistant just understands what you wanted to do. Incredible. You can't hard code that with rules. There are infinite number of different ways people can say certain things. How can you write rules around it? It's impossible. It's outright impossible. Okay, so that's again a classic example of what ML is and ML can be used for. Google Do Play, wonderful. This was an excellent video by Sundar Pichai. Please look it up. In the interest of time, I cannot play this out for you, but I'm sure people in the audience have probably would have heard about this. Sundar Pichai's haircut address. Very interesting. He demonstrates that live on the platform. Actually, he actually calls up Google Assistant and say, "Hey, Google, book me a haircut." And basically, the assistant goes and calls up live. And what an incredible conversation! Imagine where we are headed. So please do look it up. People who have never seen that ad, go to YouTube and after the session, look it up. Sundar Pichai's haircut address. So really cool, just to show you the advancements that we've done in NLP today. So here it is something very similar. But yeah, so Google Do Play is a technology that Google has created here overall. Okay, self-driving cars, again, incredible applications of machine learning where they're using a whole lot of different things, right? So self-driving cars are not only using computer vision, but they're also using NLP. They're using gesture recognition, a whole lot of different things they're actually using. Okay, it's not a simple rule-based system. Okay, it's not like I can write a set of if-else statements and I can drive a car using a simple set of if-else rules. Not really. It is incredibly complex. Okay, you have to look at a lot of different factors and you want the machine to learn on the basis of that. So these are again incredible applications where ML is used. Okay, another area where we are seeing machine learning and deep learning getting used a lot is medical diagnosis, X-rays, especially since COVID took over 2020. Since 2020, we've seen a tremendous amount of research and development in this particular field. These are all age-old examples: radiology, X-ray, CT scans, MRI scans. How can machine learning algorithms look at a picture of an X-ray and how can they predict whether a person has certain types of cancer or not? Things like that. Or maybe how can I look at the let's say there's a bullet wound that went in, or some kind of foreign objects entered your chest. How can I look at an X-ray and how can I find out exactly where those articles are actually there? So those are again incredible things. This is a wonderful example, Anil Kumble. So Anil Kumble basically has this thing called Spectacom. You can read about it. Okay, Spectacom, basically they have this smart cricket bat. They use the Microsoft Azure cloud to implement the solution, but quite incredible. This particular bat, it comes with a sensor. Okay, and basically, and it is used in academies in the country. Training academies, they use it. This has been trialed and it is actually being used. It's quite incredible. You can watch a video. You can go later on and read about it. And when you hit the ball, it can actually capture a whole range of statistics about it, about how you play and your bat speed. And typically, all of you, I'm sure people are cricket crazy fans. Most of you in the audience, because we are from India mostly, right? So if you look at players like Mahendra Singh Dhoni and all, like obviously, I don't know, we can't compare Dhoni today with Dhoni 6 years back, but his bat speed is immense. Like when he used to play the helicopter shots, right? Wouldn't it be incredible if he can track at what speed his the ball goes from the bat? The bat speed is very, very crucial in generating power. Or somebody like Chris Gale, or if you look at somebody like maybe in cricket, if you talk about maybe in Indian context today, like a Hardik Pandya, who is also a very, very big hitter of the ball, right? So these kind of statistics can really help in figuring out your pose, your stance, and all those kind of things. Okay, and imagine, let's say, Indian cricketers typically struggle a lot with the short ball, right? So again, things have changed a lot right now, but at least historically, during Ganguly's era, the short ball was very feared in Indian context. People couldn't hit the hook shot very well. Players used to fear the hook shot because we don't have fast bouncy tracks in our country, right? So how do you basically, in a net practice sessions, how do you consistently use the bowling machine to bowl short balls And how can you force the batsman to hit the hook shot? And how can you track? Like, are you middling the ball? Are you still getting the right bat speed and all that kind of stuff? So Kohli is an excellent player of the hook shot. How can you practice and how can you use this? So this is a great example where machine learning and analytics is actually used in improving your batting skills, overall. And by the way, in the world of sports, I think there's a lot of applications of AI ML that's being used today. Okay, I'm not even talking about IPL, bidding. There's a lot of statistics used there. By the way, just to clarify, that number, the bidding that happens, and which player gets what. There's a lot of predictive analytics that goes into that. By the way, is today's day and age, definitely yes, because maybe in the earlier editions not so much, but because we do have historical data as of today, a lot of analytics actually gets used to decide which player will be pick, and predictive happens, and how many runs they might score. Past tournament data, historical data is actually analyzed in a huge way when the bidding happens in IPL and other kinds of tournaments, right? Even football, and football is, I would say, leagues ahead compared to cricket, because talk about some of the richest football clubs, Barcelona, Real Madrid. Obviously, they're not so rich today. That's a different matter. But Paris Saint-Germain and all these clubs, if you see, they are doing a lot of analytics there, right? So even simple things like, let's say, Ryan and Messi penalty shootout in the World Cup, probably the biggest do or die thing, right? We all remember those World Cup finals, no? Glory days where penalty shootout, World Cup final. Imagine World Cup semi-final penalty. Which player do you put forward? It's a do or die decision for the coach. How do you decide? So historical data is actually taken into account. You want to look at the players and look at the setup, look at the goalkeeper, which player might hit where, what is the probability that if Messi hits a ball like this, he might score, and the player is actually given that information, and based on that, they will perform. So these kind of things actually happen. So it's not some science fiction as well. Soccer uses it a big way. And if you talk about one sport that has used analytics, one of the old, that particular sport that has used analytics the most, the earliest adopters of analytics is baseball, actually. You can look at it. Baseball is one such sport which has used this in a huge way. Right? I'm forgetting the name of that movie. Maybe one of you can remind me. I think Moneyball. Yes, I am. I just got the name now. There's a movie called Moneyball. Incredible movie, actually. If you've not seen it, you must. And you'll really be inspired by that movie. So how they use analytics and data science to really improve a player. Like, you look at your statistical thing, how you play, how you hit certain shots, and how you decide the player positioning and all those kind of things. So this is one of the earliest adopters of analytics in the sports context, I would say, baseball. Yeah, so quite incredible, some of these things, how they, yeah. Next thing we have, next thing we basically look at, um, Shazam recommendation systems. Generally, broadly, we have Amazon Prime, we have Netflix, we have all these platforms where you list Spotify, obviously, where you talk about songs, you talk about movies, where you watch a particular you talk about a particular movie and it recommends similar movies to you. Again, they are classic applications of machine learning, incredible applications of ML, where you get personalized guidance on the basis of what you watch. And again, if you see, these cannot be hard coded with rules. And these are, again, things that invade everyday lives. We are all using it. YouTube, you watch a particular video, the very next session that you start, if you refresh your page, you get a very different set of recommendations on the basis of that. Quite incredible, actually. And it is personalized to every user's experience. Even social media platforms, if you see, LinkedIn, for that matter, if you see jobs recommendations, everything that you get there in LinkedIn, again, classic examples of machine learning. Even if I just talking about LinkedIn, if I just show you, really interesting, actually, if you see, even the recommendation that you get, the jobs recommendation that you get, and all of it that you basically get to see. So if you look at this entire LinkedIn page, and if you look at the kind of recommendation that you actually end up getting overall, let's say if I open up the jobs page and if I see some of the recommendations, so these are all recommendations that you will get based on, based on your profile and based on the kind of things that you you are basically accounted for. Okay, so maybe it is showing me a lot of these job roles in data science, product manager, manager of data science, senior director of data science. Okay, maybe it's making me very to apply. Anyways, but then you can see that how incredibly LinkedIn is actually doing recommendation. This is also a classic example of recommendation engine overall. So the only difference is basically, in the case of Netflix, it is recommending movies to users. In the case of Spotify, it is recommending music to users. In the case of Amazon, it is recommending products to users. In the case of LinkedIn, it is recommending jobs to users. Just what you're recommending is changing, but the technology stack internally is remaining exactly the same. In the case of Facebook, the entire news feed that you're able to see, it is recommending the different news stories to the different users, and the entire news feed is personalized actually. So quite incredible how the whole thing is actually working overall as we speak, right? Okay, incredible stuff actually. There's so much going on in this particular field. And another thing I would like to clarify is the entire aspect of conversational chatbots, which have picked up a lot over the last few years or so. I think all of you, we are all regular users of Zomato, Swiggy. Maybe even if you go back a few years back, the systems were not quite developed. But if you look at today, I think the systems are very well developed today as we speak. So you even simple things like let's say the order got delayed a little bit and the food didn't get uh, uh, the food didn't get delivered as a batch, on time. You can actually raise a support ticket or a query. Maybe this was 2, 3 years back. Swiggy will connect you to a support agent. Today, as we speak, Swiggy will give an automated response to you. And even you can get automated refunds up to a limit. Obviously, people misuse it sometimes, but there's a limit that they put in. But up to a point, you can get an automated refund. If you say, I got a incorrect item, Swiggy will ask you to click a picture. And if that picture matches with that item that you sent, they will use some amount of computer vision to estimate that, okay, this is the same item and all that. And based on that, Swiggy will automatically give a refund to you. Okay, that's one of the ways you can look at it. And Swiggy has enough money to give refunds. They're running on losses, although they are all investor money. That's another matter for Indian startups today, right? All running in losses. That's the business thing today. Anyway, so this is pretty much how the whole thing can be summarized, how machines basically become better. So AI learns from experience, more data, better models, and this is how we are looking at the whole thing. Instead of hard coding static rules, the machines learning from lots and lots of historical data, just how children learn, and the more the data, the better the models. Okay, new data comes, the model improves. New data comes, the model improves, and this is a general way to look at how we build systems using machine learning, right? Now, talking about computer vision, which is a really exciting space, I want to talk a little bit about that because we have so much going on in computer vision field, in the vision domain generally. There are a lot of different types of problems that you basically have in computer vision, right? We have classification problems, we have localization problems, we have detection problems, and we have segmentation problems overall. So, what is the classification problem? What are you actually doing in classification, right? You look at a picture of a object and you try to predict what that particular object is. That is what we basically refer to as classification. Okay, so classification is basically a term that you use for you look at a particular object and you try to predict what is that object. So you look at this particular thing and it's a cat. Localization is where you try to put a bounding box around it. You're doing two things. A, you're trying to find out what is the object, and B, you're trying to find out where is the object. So two things you're trying to do in localization. So A, you're trying to find out what is the object, and B, where is the object in the picture. Detection, very similar to localization. This is one more, it's an extension. The only difference is in detection, you're looking about multiple objects. Okay, so again, you're asking the question that, hey, where are the objects in the picture? Put bounding boxes around the objects, and what are the objects in the picture? So we're looking at a dog here, a cat here, a cat here, a duck here overall. And this is again something that is very commonly used in many of the modern smartphones. You try to take a camera, you try to take a picture, and automatically the faces are automatically detected. So Facebook is one of the earliest adopters of this technology. Going all the way back to 2009-10, Facebook was already doing this photo tagging. You go to Facebook, you take a photo, and you try to tag that picture. Try to hover over that photo, and Facebook will automatically put rectangular bounding boxes around those, around the faces. Not only that, Facebook will even, if you try to tag that particular picture, Facebook will also give the nearest estimate as to who that person might be, which is quite incredible. So not just it will put a bounding box around that face, but it will also try to, kind of estimate who that person might potentially be, which is quite cool actually in that context. So again, it's using machine learning technology that is doing, and these have been there for decades, not like something new that we're discussing right now. Okay, I can say that this technology is also extremely popular in the surveillance and security space, basically, where you're talking about airports and CCTV cameras overall. And if you and if you look at from that particular perspective, how can you look at the CCTV footage of the airport or a particular locality, and on the basis of that, how can you overall go back and try to figure out who the people are, where the objects are, and what it can be. So this is again a great example of detection you can look at. Okay, and in the COVID context, I think another application of this that came out a lot was PPE kits. Like airports across India, they already have it. Airports globally, they have the system. Okay, where if you're trying to exit out of the airport, the models will basically put a bounding box around your face, and they will basically do the temperature check. So detection technology is already in use in Indian airports. All the major airports already use it today, and also workplaces, hazardous workplaces, right, where you're required to wear helmets, you're required to wear masks, you're required to wear. Okay, detection technology can be potentially used there also, where we can put boxes around the person and try to find out is that person wearing a helmet, is that person wearing a mask, and things like that. Okay, there was a company called Landing AI. I'm going to give you an interesting case here that came up with this very interesting thing right in the middle of COVID. This was back in April 2020 when the world was a different place. Okay, the world is a lot better today, much better. Okay, things are opening up, which is a good sign. But April 2020 was probably a time we would all like to forget. Okay, anyways, so if you look at it, this is what Landing AI actually did. They actually developed a AI social distancing detector demo tool where the camera footage from the CCTV was taken, and based on that, they try to estimate effectively where the people are and are the people following social distancing guidelines. So very interesting, and these have been trialed in a few workplaces also in a way, and you can see that they'll try to go back and put bounding boxes around the people, and they'll try to also, if the people are too close, not following that 6 feet distance, the models will automatically flag a red. And based on this, you can potentially do contact tracing and those kind of things, which are happening a lot back in those days, because people were very fearful of COVID. Not so much now, obviously, but yeah. So these kind of things could be done potentially if you see. So this is completely using detection technology right now. Okay, and model is prone to mistakes. He didn't identify the person here, so machine learning is prone to errors also as we speak. So these are again a couple of incredible examples and applications we can basically look at. And then finally, we have something called segmentation. If you look at segmentation overall, segmentation is again very similar. So the segmentation concept is again very similar to detection. The only difference is that in segmentation, you basically in segmentation overall, what happens is you don't exactly need to put precise boxes. I'll give an example to you. So conceptually, segmentation is very similar to detection. Detection, you're trying to put exact bounding boxes around the person, whereas in segmentation, you need to put you don't need to put exact bounding boxes. You need to put more of exact contours, exact boundaries you are going to put. Because the problem with bounding boxes is that bounding boxes can basically be incorrect. There can be a small margin of error that can also happen, right? So that's one way to look at bounding boxes. There can be a small margin of error that can happen. But in detection, that will not be the case. And if you look at more sensitive applications like self-driving cars, especially, you cannot do detection here. Like, for example, if I ask you, where is the person? Like, I can't put a bounding box around this person and say, okay, there's a person here. I can't put a bounding box and say there's a person here. So it's very difficult because there's a small gap that you leave here. And if you think from the perspective of a footpath, I can't put a bounding box and say, okay, there's a footpath here. This is the footpath. No, we can't say that. We can't say there's a footpath here. No, we want to put the exact boundary around the footpath so that when the car is driving, the car knows exactly what the contours of the footpath are. And that is exactly where segmentation comes in handy. So technically, they are all computer vision problems. They're all problems involving images and pictures, but these are all different avenues of computer vision problems that we're exploring overall. So when the car is driving, it knows exactly what the boundaries are. Okay, segmentation also has very nice applications in the field of the medical diagnosis, where if you're looking at X-rays and if you're looking at small tumors and other kinds of things, you don't want to put a box around that thing. You want to put an exact boundary around that particular tumor, and you want to say exactly what happened and how it, like exactly the contours you want to point out, so that when a attending physician is going to look at that particular entity, the physician has very good guidance and very good understanding as to what they're looking at. So that's the again the general understanding behind what segmentation actually is, right? Now talking about detection, wanted to show you this really cool demo. So a lot of different kind of things we can do. So it's very exciting stuff, obviously, and just wanted to quickly show you one small demonstration of the thing. I need to turn off my webcam for a second because, excuse me, this is going to use the other camera. And if I just show you, it's quite cool. And you can see just one small example of detection. My live webcam feed, if you see, it's going to come up in a minute. And if you, this is just a small example. I'm just saying, like, what it's trying to do is it's trying to do some kind of eye tracking right now for me, right? So you can see this kind of things could be potentially very useful, especially in the context of, let's say, examinations. If you look at the whole online examination, context, like, how do you ensure that people don't cheat, right? So maybe if I can build accurate models to track a person's eye, I want to ensure that the person is exactly looking at the screen. If for a 5-second, 10-second period, the person is looking slightly this side, the eye tracking things will actually kick in. And if the model is reasonably accurate, we can estimate that the person is probably cheating. And this could also be very relevant from an interview context. Like, online interviews are so difficult. Like, how do you ensure that if you're asked a question, you're not looking this way or that way, and you're looking at the answer and answer it, right? So eye tracking systems can come in very handy potentially in this case, right? You can also see the model is not perfectly accurate. So somehow it is thinking that the eye is there. Obviously, it's not an eye; it's a light that I have in my room. So this is, again, that goes to show how inaccurate and sometimes how error-prone machine learning systems actually are. There are a lot of these pre-trained libraries and all that are available, using which you can do some really cool stuff in ML overall, right? I wanted to show you one more very nice example, using which we can. This one is actually using an object detection model called YOLO. YOLO is a very popular object detection model that we generally have, and I wanted to show you a very quick example using YOLO. Let's see that. And these are all pre-built models I'm actually using, so nothing too special about it. Very simple. I'm not trying to create anything new. I'm trying to use something that is already available. Okay, so let's see. I'll quickly go back and open this up and show you. So I'm going to run this for a second. It's going to take a minute here. I think, Ravi, that question is very subjective. Sorry, I'm going to take it up a little later, but I think it's very subjective what is right and wrong. So I think there are more technical metrics that are involved, and one is the ethical aspects of should you do machine learning, and the other is basically the accuracy metrics, that whatever solution you build, is it a right solution or not. So I think a lot of it has to do with those aspects, which are a little bit more technical in nature. Yeah. All right. I think momentarily just took up that question. But if you see, the model has predicted the person with 100% accuracy. And it is a detection model. If I point out my remote here, see, the model has identified a remote here. Okay, it's a remote. It's not perfect, but you can see there's a 90% probability it's a person, and there's basically a X% probability we're looking at a remote right now. Probably works pretty well. I can look at my cell phone right now, and I also have a chair there. I also have a laptop there. But my camera resolution, I think, is a little poor. This is my inbuilt camera I'm using. But you can see the chair is identified with 98% probability. I'm a person sitting here, and I can also say my cell phone here, and the cell phone will also be identified here. Okay, let's see. All right, not perfect, but it identifies that cell phone. Maybe, I'm not sure. The bottle probably we can also hold, and it will actually do detection of the bottle also. The bottle is also working pretty well. Okay, again, the reason why you're able to see some amount of error coming up right now is primarily because the resolution of my camera. That's the only sole reason. Otherwise, if the camera quality was a little better, the model would have been a little bit more accurate. If I just slowly turn this side, I have got one more chair here, and the model will identify it's a chair also, right? So it's another way to look at it. Yeah. So it works quite well. Works quite well generally. Okay. So detection, you can see that there's so much you can actually do. So much you can actually do with it. And in case you're thinking of applications that you can use in your home itself, and it can be done if you're curious about it, it can be done where you can probably build these models into your cameras, and probably using that you can go back and identify in the midnight if you see any people coming. Detection models can identify is this the person climbing up the terrace or something of that sort. Immediately alarm will be sounded, and you can probably be a little bit more alert that, hey, who is coming to my house such late in the night? One way to look at it. Yes. Not really, Aniket. That was actually an example of an error in machine learning. So that's not exactly yeah, that was more of an error, just to clarify. Yes, that was more of an error what you actually saw there, just to clarify. Yeah, that was not exactly Right. So yes, it should not have detected the bulb holder and the curtain holders and all that, but those were primarily errors that we saw. Okay, just to clarify. Yes. All right. And talking about segmentation, another very interesting application that I wanted to show you. This was actually a very this part of a large-scale Kaggle challenge that was actually held. Again, just to show you how incredible these kind of how overreaching uh, uh, these solutions actually are in the field of ML. So you can actually see that this Kaggle challenge that we're going to see, where the segmentation model is actually used to track salt deposits beneath the Earth's surface. Again, this is a bit of people who have actually worked in the oil and gas industry will understand this, that salt is a very major, a very important factor in determining needs to be checked to understand whether you should drill in a particular spot or not. And we're talking about oil exploration, so it's billions of dollars at stake. And you've got a lot of heavy equipment, a lot of heavy machinery that you're bringing in, and you need to be very sure that the exact spot where you're drilling, does that spot contain oil? You need to be very sure. And so detecting salt is actually very, very important to understand, the risk factors. And we actually can use segmentation technology, where using segmentation models, we can actually very accurately predict whether the particular where there will be salt and where there is no salt, and we can identify those factors. And this is actually part of a very live Kaggle challenge that we have. I won't be discussing the technical details, obviously, in the session, but just to make you a little interested and just to show you how overreaching these applications can get. We're talking about things which are potentially going to cost billions of dollars over time. Machine learning is being used as we speak today. Or something like an MH370. That is a disaster for, we still haven't been able to solve. Mysterious Malaysian airlines that got lost, and even still we are finding debris. And machine learning is very actively used, although without any success. But how do you basically use satellite images, and how do you basically use detection technology to figure out, missing? Because searching for a plane, it's like finding a needle in a haystack. It's impossible. The ocean is so huge. Although we think that, okay, send ships and scan the area, there's no way you can do that. It's impossible. So the only the only solution that we have here is potentially using high resolution satellite imagery and trying to use computer vision models to see if we can detect some parts of the aircraft on but obviously, if that is submerged, then we need to get the underwater data and try to use machine learning to detect that if we can find any debris. But machine learning is being used in a huge way in that space as well, by the way. And even the current Ukraine-Russia conflict, if you see, like how you are able to see the the satellite images by some of these commercial satellites, right? I think Maxis and all that you have. So they are using a huge amount of computer vision, right? So military, I mean, obviously these are things we don't talk about, we don't generally get to read about, but military is one of the biggest users of AI today, right? Artificial intelligence, whatever we are talking about, we talk about missile defense systems. Russia has the S-400, Israel has Iron Dome, right? US has Patriot missile defense systems, right? So these are some of the most advanced use cases of AI you can find, right? The internet came from DARPA. All of you know DARPA. That's a defense research wing of the US Army. Okay, and so whatever applications of AI ML we are seeing today, and we are maybe implementing commercially, so US Army already has those things today, right? I mean, I'm saying US is the only country who has it, but then generally the Army has a tremendous applications of machine learning that they're using today. Okay, simple. And I'm not saying simple. Missile defense is not simple by any means. It's an extremely complex problem, by the way. So how are using drones, and drones are using a lot of computer vision there. And if you've read about these fighter jets, okay, so fighter jets, the kind of helmet-mounted displays that pilots wear, there's a tremendous amount of computer vision that people use there also, where you're able to look at the terrain, and you're able to, it gives you real-time augmented information about things in the terrain. As a lot of vision technology is actually used in that space as well. Generally, so incredible applications we have, and we can keep going on and on about it. So do read about it, military, and how they. If anybody is fascinated about, yeah, what is here. All right. Am I saying that? I'm not saying, everybody's saying. I'm nobody to say that. Everybody's saying that it's popular. And it has a lot of use cases. Well, who am I to say that? It's popular. It's a known fact, right? There's a lot of use cases you have in this field. Not something I'm saying. Okay. All right. And finally, I would like to quickly, show you another very, very interesting space where we are seeing AI and ML and deep learning solutions that are being used, and you can see incredible applications. And everybody in this audience, you have used FaceApp, right? It's really incredible. Like you take a picture and you can actually make yourself look something else, something entirely different. And how do you think it happens? Well, welcome to the world of deepfakes. Very complicated technical idea, but very exciting concept, generally speaking, right? Where you can basically take any picture, anybody's image, and you can make yourself look like anybody else. I mean, I can make myself look like Tom Cruise, right? So, like what? If you have heard of these videos where Obama is speaking something, you can put words in Obama's mouth. You can put words in my mouth, probably, but don't do that. Don't do that. Like you can basically take my picture and you can put words in my mouth, right? You can make me say something using deepfakes today, right? So that's that technology we have today. Now, reverse engineering is also possible. Like, obviously people who want to harm, they can harm, but you can always reverse engineer. You can always figure out that, okay, what actually happened and all that. So that's also possible. So deepfakes are also incredibly powerful. In case there is there's a wonderful website I would like to bring you to as final thoughts for this particular session, almost 2 minutes over time. So there's a wonderful wonderful site that I wanted to bring you to.
Thank you, Sayan, for this most
Sorry?
fascinating hands-on session.
Uh, yeah. Just one last point I wanted
Yes,
to just
please go.
mention. Yeah. Sorry. Yeah. I know we're almost out of time. Actually, this is the one I was referring to, guys. This is incredible, actually, where we are. Yes, actually, you can see that this is a random face generator, actually, and it's actually very scary. If you look at human faces, this is the realistic face. This person actually doesn't exist. Now, all that you have done is you have manipulated the pixel patterns and generated a face of a person. This is using deepfake, actually, completely. So they use a specific uh, uh, specific technology called generative adversarial networks, and you can basically generate faces, refresh the image, and you can get a different face. Now you tell me these faces look so realistic, right? But they are not real faces. They're completely generated faces we're looking at right now. Okay, so again, you can think of how you can probably create social media profiles and whatnot using these kind of pictures. Not very difficult to right click and save that picture and create a profile out of it. So there are so these are all very incredible things to talk about. But then the other aspect is basically where how society uses it and where we are headed with this thing. So deepfakes are another entirely different thing altogether, and lot of incredible applications we see in that field as well overall. In case people have heard of examples where AI has created pictures, AI has created music, AI created audio, AI created video. Okay, AI has created even a thesis for that matter. A few months back, a few years back, this news came out where AI can even create entire thesis for that matter. AI generates text. So these are all examples of generative adversarial networks or GANs. We're talking about a very specific kind of networks which are called GANs. You can read about it. Just wanted to mention it a little bit more technically here. Very exciting field of research as we speak today. Yeah. All right, wonderful. I think with that, I will overall, yes, AI paintings are also very incredible, actually, Anand. Yes, yes. So I think I will basically bring my general conversation to an end, and I think I'll hand it over to the team. Yeah.
Thank you, Sayan, for this most fascinating and hands-on session. Yeah, we all, I'm sure, we're excited to be a part of this session today, and it has helped us understand the complex world of AI, ML, and deep learning. The case studies, examples, and live demos made it easier to grasp the beauty and positive impact that these applications are making to modern-day businesses and on our everyday lives. But with a strong caution that sometimes analysis can be misleading due to incorrect, biased, or insufficient data. For companies to get the optimum use out of these technologies, data collection analysis is the key. This will help them constantly innovate and improve their offerings to address real-life problems. I would request Sayan to please take up some of the questions posted on the Q&A tab by our students, or maybe I can read them one by one.
Sure, I can take it up, absolutely. Basically, yeah. So are there tools to identify deepfakes, Ganesh? Yes, there are. I think, as I said, the same generative adversarial networks that you use to generate deepfake models, the same GANs can be technically used for I would say reverse engineer it, and you can actually do that. So it's a bit of a technical thing, but you can do that in a way. So that can be done. Yes. When I say error prone, Sudhanshu, it's a general term I use. Error prone means it's prone to errors, it's prone to mistakes. So unlike rule-based models where it's like which are more static and more accurate and flawless models where it's like programming, right? So error prone is more like it's prone to mistakes, it's prone to errors. That's a general idea. Yes, yes, yeah. So can you give an example of DL that we use in our life? Firstly, I assume Google Lens is DL. No, not really. Vagish, as I told you, remember I said deep learning is a subset of machine learning. So technically, it's machine learning itself, but I would say generally speaking. It's in a way deep learning in a way, right? So obviously it's a subset of machine learning. So it is deep learning because it's working with computer vision. Okay, so deep learning is a subset of ML. So I would say it is deep learning, but it is also machine learning in a way. So more advanced ML is what we call DL. What I took up in the initial part of my conversation. You might want to go through that recording a little bit. Yes, yeah. All right. Yeah. Are deep learning and regression models applicable in trading and financial investing? Oh, that's a very good question that you ask, Ravi. In fact, as we speak today, we do have incredible applications and competitions that are happening where, we look at crypto currency forecasting and some of the major top investment banking companies or funds. We have pricing models, trading models. If you look at all these big fund managers who are managing mutual funds, they've got a whole army of traders who are working with them, who are analysts, who are actually working on the modeling side of things. So yes, indeed, there's a tremendous amount of machine learning that is happening in this particular field. Yes, absolutely. So is it 100% accurate? Of course not. Nobody can predict a Ukraine conflict. Who will predict what will Russia do tomorrow? What all markets will go tanking, oil will go where? How will you know? So, again, COVID 2020, April 2020, nobody can predict. So these are again instances that nobody can predict. But yeah. So obviously, up to a certain extent, these are pretty accurate. LSTMs and all are pretty popularly used for. Primarily, LSTMs are used in this time series forecasting site. Yes. Yeah. Yeah. Okay. Okay, so I think I'm not taking the career related questions generally. I can see a lot of career related questions. Gayatri, WebHub, maybe I think we will plan a separate career session later on generally. But I think the drive is the key. You are all in this particular domain at the right time. I think there's a tremendous amount of hiring that is happening in technology overall, and I'm so closely associated in this field, and I think there's just a huge talent crunch that we are facing. I think it's just an amazing period to get into this domain. Doesn't matter what background you have, doesn't matter what you did, where you come from. We can't change our past. No point thinking about it. No point regretting about it. I would say look at the present, learn things, and get ahead in your life. Okay, so that's one way to look at it. Yeah. Okay. And this is so relevant for people from other domains also. Like sometimes people are like, okay, I'm doing this. I've got this background. I've done this particular work. But I can tell you. With my experience with organizations, generally today, especially today, we are seeing organizations are very liberal in considering people from other experiences because you don't have people. You don't have people. Good people are leaving. You need people to do the work. I think at the end of the day, you can't be absolutely steadfast in saying that, okay, no, we want people with X amount of years of experience. You can't have that. The organizations are becoming much more liberal in terms of considering hands-on experience, even if you can show something in terms of projects and some other secondary skill sets that you've developed through competitions and hackathons. I think that's amazing, which is, I think, where some of these courses come in handy. If you can participate in some Kaggle hackathons and all that, which is good, and that is also considered. Yeah. All right. Right. Yeah, machine will not determine what algorithm to use. That is something that it's your job. You have to use the tuning methods. You have to compare different models, and it is kind of something that you will have to do, Dipanshu. Yes. Yeah. I would say yes, Sudhanshu. Do you think a website or a mobile application can be an example of AI? I think you mean to say example of AI. Right. So it's an example. I think So example of AI. I believe that's what you meant. So in a way, yes, when you develop a mobile application or a website, you specifically hard code rules as to how the application will behave. So it's a rule-based AI primarily. So Facebook, when you want to sign up for the web page, there's a specific set of rules that come in exactly on how it is going to work and all that. So, yes, so that's one way to look at it. Yes. Yeah. So if you change the code, Anvesha, you're still doing it in a static manner. Just to clarify, with your question, if you're doing it, you're still doing it in a very static manner, right? So yes, yes. So every if-else program is technically AI. So anybody who's ever written a program, you're all AI developers. Although you can't claim it in your resume, but in a way it is. You're writing a script, you're writing a program, you're giving the machine a set of instructions, and that's how the machine is actually working in a way. Yes. Okay. I would say, it's an incredible question, Madhusudan. I'm not getting too much into that, but what you have actually asked right now, the chess engines part, incredible question. You can read a little bit about AlphaZero and AlphaGo. I would say it's more into the world of reinforcement learning. See, it's a subset of machine learning, but that's actually using reinforcement learning. If you've heard of AlphaGo and AlphaZero, uh, we have AI agents today that can play chess very well. So yes, we do. We did have IBM Deep Blue that did defeat. So that's Gary Kasparov in that chess game. That's one thing. But after that, you had Google DeepMind, which came up with AlphaGo and then AlphaZero, which is a chess thing, and they are very, very accurate. They actually use machine learning and a specific subfield of machine learning called reinforcement learning to learn how to play chess. It's not through data, but you show the agent the rules of the game, lots of historical games that they have played, and it just learned how to play chess. It's very accurate in a way. Yeah, so that's there. Yes, so I would say in a way it's reinforcement learning. Read about DeepMind and AlphaZero. Yeah, it's quite incredible. Yeah, I would say in a crime domain, AI ML has a lot of applications, Meenakshi. So I talked about cyber, depends on what kind of crime you're talking about. Cyber crimes obviously can be tracked using AI ML. And if you talk about security surveillance, huge. I would say even in India, if you see Delhi is probably the most heavily monitored, cities in the country. So many CCTV cameras are there. Where is it going? It's going to a central station. It's being used. It's being monitored. And a lot of machine learning is actually happening in that space. Talk about airports globally. Talk about places like Singapore, London. So at a city level, how do you basically look at the camera footage? Even simple things like unclaimed baggage. Like there's a public place like a airport or a metro station where somebody has left a bag, and how can the camera basically put a box around that bag and say that, hey, you know what, this looks a little out of place, where person has not picked up the bag for a long time and this looks like an unidentified object. So these are again applications where it can be done. Yeah. Not really. Yeah, so IoT will be more of a application. IoT is more of a general Internet of Things devices, but you can integrate machine learning and deep learning in IoT. You can do that. I mean, if you talk about IoT devices, ML can be integrated overall, connected devices overall. So I mean, I can say even something like a smart fridge. Okay, something like a smart fridge that can be a smart appliance, internet connected device. So then I can incorporate ML in that. I can make that fridge respond in a certain way based on um, how I'm basically driving, around. Like I don't know, like probably you can say that your car is connected to your smartphone, your fridge is connected to your smartphone, and based on how much you're talking, maybe the model will understand, okay, you're very hungry, and something of that sort. Like when you come home, probably it will predict, okay, you want this. I know that's probably thinking way too much into the future, but this could be potential application. So IoT is a different technology stack, but you can effectively uh, induce ML and deep learning based things in IoT devices. Yeah. Okay. I would say the scope is massive. I think it's just again, as I said, I'm nobody to answer this question. It's just out there everywhere. Everybody's saying that. I'm only one of the people, one of the practitioners in the field. So I would say this everywhere. It's not something that I'm saying that where ML will AI will go in the next 10 years. But I think if you look at advancements that we are making in the field of AI ML, especially with Elon Musk, Neuralink, what they are trying to do with the human brain, look at the brain signals and trying to predict what a person might be dreaming, what a person might be thinking, I think it sounds scary, I would say, probably. I don't know. I'm very excited and at the same time scared where AI ML will go in 10 years overall. I mean, if you can decipher a person's brain signals, I don't know, that's incredible, I would say, probably. So yeah, so maybe this technology shouldn't go in the wrong hands, but it's quite exciting, yes. Yeah. Okay. So I think pretty much taken most of the questions, guys. I'll probably pass it over to the team now. And thank you so much for being a part of this session, guys. Yeah. Really enjoyed interacting with all of you, and been a pleasure, absolutely, to be a part of this session. Always love talking about it. Been a very tiring day for me, and still I think it never feels tiring when I talk about this particular domain. So it almost feels like it's such an incredible interaction with all of you. Yeah, thank you so much for being a part of this session overall. I'll pass it over to the team now. Yeah.
Thank you again, Sayan. It was great having you with us today. The audience, we are sorry we could not address all 100% of the questions due to paucity of time, but we keep scheduling these sessions, and please feel free to attend them in future. A big thank you to all of you for attending today. It's been exciting to see the level of participation. You've been a great audience. Before you leave, please provide us with feedback on the webinar by filling out the survey as you exit the session. A recorded version of this webinar will be available on our Online Manipal Facebook page if you wish to view it again. You can follow Online Manipal on social media to stay updated on our programs and industry expert sessions. Thank you again for attending, and have a good evening. Thanks a lot, Sayan.
Oh, yeah, sorry, I think thank you so much. Yeah, take care, all of you.
Thanks. We loved your talk.